Let's do some math. All right. I think you would have been okay with the next pattern in the figure. It would have been a 4x4 on dots. Number 2 would have been five pieces, right? Or what? Next pattern, 3, 6, 9, 12, 15, 18, 21. And I know the answers are there. Is there any from 3 to 10 on the front of 2.1? Yeah? 8? Okay. So this is problem number 8. We have 2, comma 1, comma 2 over 3, comma 1 over 2, comma 2 over 5, comma 1 over 3. And we want the next 3 spots, right? So, okay, so taking a look at it. We see a pattern right away? Yeah.
Just asking a question really quickly. Isn't there like a equation where you can find out?
So it depends. And if it's arithmetic and geometric, absolutely. If it isn't, then you just sometimes you have to look for the pattern. So let's make everything over 60. So 120 over 60, that's the same thing as 2. 60 over 60 is the same thing as 1, right? If that's over 60, that's 40 over 60. I'm just seeing if maybe I could, what is that? 30 over 60? 24 over 60? Oh, 60, get in there. And then 20 over 60? Maybe that works for us. I don't know. Let's see, that's, so it's a difference here of 60, 20, 10, and 6, and 4. Did I do that right? You got a pattern there? 60, 20, 10. 6, 4. I don't know. Does anyone see a pattern? I know the answers are back there, but is there a pattern? Did I write it wrong? I did? Oh. Because that's always possible. Number 8, it says 2 over 7. So we go to 2 over 7, and then 1 over 4, and then 2 over 9. Anyone see the pattern?
Oh yeah, I know.
What do you got?
So when you subtract from going from 1 to 2/3, it's 1/3, and then when you go from 2/3 to 1/2, it's 1/6, which is adding 3 to the denominator, and then going from 1/2 to 2/3 is 1/10. So adding 4 to the denominator, and it goes on. 4, 5.
Okay. So say that one more time.
So the denominator of the changes by 1, and it starts off with 3.
Starts with 3. So it's 3 minus 1, you say?
No. So 1 to 2/3 is 1/3.
1 to 2/3, that's 1/3.
And then the next one is 1/6.
1/6.
And then it's 1/10.
10.
So you go from 3, 4, and then.
So it's 3. It's 4 more.
And so the next one is 1/15.
1/15. That's 5 more. And then is that 1/21st?
Yes.
3, 4, 5, 6. And that would be 1/24th. We're going.
6 and then 7.
Oh, 7 more, so 1/28th. Wow. Holy cow. That's crazy. Okay. I don't think I'll give you that much of a curveball on a test. What else from that page went up to number 10 on 2.1? Number 10. so that should be 125, 216. That's 1 to the third, 2 to the third, 3 to the third, 4 to the third, 5 to the third, 6 to the third, 7 to the third is 343. Is that right? Huh. It's just perfect cubes. All right, flip side. Anything from 11 to 20 on the backside of 2.1 that we would like to go over? Yeah. Number 12. Oh boy. Number 12 says the quotient of two whole numbers is always less than either number. The quotient of two whole numbers, whole over whole, is always less than either number. It's always less than either. So I think if we did like 1 over 2, it's less than 1 and it's less than 2. I agree with that. But what if we did like 7 over 2? 7 over 2 is less than 2? No. What's 7 over 2? 3.5. This one's not going to work. And this one works. So this one doesn't work. So is that a counterexample? Okay. So I would say our counterexample would be if we have a improper fraction, doesn't hold true. Is that okay? Does that make sense? Yeah.
So I did the same thing but with 4 over 2.
Oh, absolutely. Perfect. No, I mean, the thing is, like, if you find, I immediately thought, okay, as far as fractions go, it seems logical if it's just a regular fraction, 3 over 7, totally works. So I thought maybe if it was a mixed number, so, or if it could be written as a mixed number, which is an improper fraction, I think that's definitely the case. Anything else up through number 20 on 2.1? Yeah. 13. The product of two numbers is always greater. So the product of two numbers is always greater than A
The 0 is one of them.
I was just thinking that. So if we had A times 0 or B times 0, that's going to goof things up. Okay, so I think the 0. So how you might see that where they might get you is they might call it the product of two counting numbers. Counting numbers, if you remember way back when we had number systems, we were naming it as 1, 2, 3, 4, 5. So that might hold true. It's called it counting numbers. Yeah.
Can you use like -2 times 2? And then -4 is less than.
Oh yeah, two different negatives. That might work too. Good. So there's a couple of counter. I like it. Good deal. What else we got up through number 20? Yeah. 14. The square of a number is always greater than or equal to the original number. Square of a number is always greater than. So 0 squared and equal to. That works. Thank you. Okay. Eugene, where you at? Eugene. Yeah. All right, so the square of a number is always greater than or equal to the original. So even if you took like a negative number, like -2 squared, that'd be +4. Ooh, the negatives. The negatives work?
Yeah.
Yep. Cool, okay. Yeah,
Couldn't you also do like fractions?
fractions. Ooh, let's try fractional. Okay, so if I had 1/2 is A, 1/4 is great. No, you're right.
Oh, yeah.
Fractions aren't going to work. There's your counterexample. Good. So fractions that are between 0 and 1 won't work. All the other fractions would be improper fractions, which are mixed numbers, which those probably would work, but that would work. Anything else on that page? We've got on factoring? Yeah. 15. The sum of two squares of the square of two numbers is equal to the sum of those two numbers. A squared plus B squared, is that equal to AB quantity squared? So if we called A equals 3 and B equals 4, that would mean that that would be 9 plus 16, that'd be 25 over here. Is that equal to 49? Because that would be 3 plus 4, which is 7. That's not going to work. So that right there is, that's not going to work for you. Sum of two squares is not the same as the quantity squared. We good? Happy day? Hey, we figured out the locker problem?
I'm working on it.
Yeah, baby.
It's hard, right? And I don't know the equation. So.
There isn't an equation.
Yeah, sure.
I'm just telling you. I saw some kid over the weekend opening and closing lockers. So as I walked by, I started, saying random numbers as he was trying to count. I'm just kidding. I'll give you the answer to it at the end of this. Cool? Just don't tell my next period class. All right, worksheet 2.2. Write each as an if-then statement, then decide whether it's a conditional statement is true or false. Okay, so problem number 1 says if two lines are parallel, then they will never intersect. If two lines are parallel, then they will never intersect. If it's biconditional, it would mean if two lines will not intersect, then the two lines will not be parallel. Seems true. We need to go over 1, 2, 3, or 4? Do you feel okay with making the conditionals? Yeah.
2.
2. The sum of two even integers is always even. If you have two, let's see what's the answer we're going to say. If two integers are even, then their sum is even. And if we need to make sure the contrapositive is true. So if the sum is not even, then the two integers are not even. I'd say that could be biconditional. We okay on 3 and 4? Yeah.
On 4, the answer says that it's false, but
Okay. If angles that are supplementary always form a linear pair, I'd say the reason that it's not going to work is linear pair is going to look like this, which is supplementary. But then I could say I have this angle here and this angle here, which are two completely different angles. And so those are also supplementary, but it's not a linear pair. Is that okay? 5 through 10, any of those you need me to do? For each conditional statement below, write the converse, inverse, contrapositive. If possible, decide if each new statement is true or false. Any of those you need me to go over? I know I went over them kind of quick, but I had fun with them. Yeah. 5? Okay. So number 5, they're just saying if A, then B. So that's our statement. And then we have our converse, which was pointed out to me that that's a pair of shoes. That's if B, then A. So we're just flip-flopping our hypothesis and conclusion. Okay? And then we have our inverse, which is the nots. If not A, then not B. And we're going to say that this means not. Okay? And then our contrapositive, if not B, then not A. So as far as things being true, the statement is always assumed to be true. The contrapositive also has to be true. We can't decide if those are true or false in this case because we don't know enough of the argument. Okay? So as far as questions would go with this, statement and contrapositives will always be true. Yes, you can create a statement that's not true, I agree. But as far as this kind of logical thinking goes, you need to know that the statement should always be true. Okay? And then if the converse and the inverse are also true, that means that you could create a biconditional statement using if and only if. Okay? 6, 7, 8, 9, 10. Any of those? Yeah? Go. Say. Speak. Yes?
Okay.
9. Number 9. If x squared equals 36, then x equals 6. That's our statement. Okay? And then our converse, if x equals 6, then x squared equals 36. Then we could do our inverse. If x squared is not equal to 36, then x is not equal to 6. And then our contrapositive, if x is not equal to 6, then x squared is not equal to 36. Okay. So we need to think that this is true. If that's true, this has to be true. Okay. If x equals 6, then x squared equals 36. X equals 6. I think that's true. If x squared is not equal to 36, then x is not, I think, what do you think? I think that's true as well. If those are all true, we can write it as a biconditional statement. Which was false? Converse true, inverse true, contrapositive false. If x is not equal to 6, then x squared is not equal to 36. X is not equal to 6, then x squared is not equal to 36. I think that's a misprint. And this is why I'm going to say it's a misprint. If the statement is true, if x squared equals 36 and x equals 6, I guess this is, oh shoot, you know what? Could x also equal negative 6 in this scenario? Could I go negative 6 quantity squared and get 36? Okay, so that might then leave that we would have to say that would be false. And if that was false, then that has to also read false. So the statement and the contrapositive have to be the same, which I guess they should have labeled it as, I guess they should have stated that the statement could be false. But when you're doing this type of math, your statement should always be true, unless you figure out something that doesn't work. Okay? Other questions on any of those off to number 10? Are you okay? Backside? 11 through 15, any of them?
Um, 11.
11?
It says that it is not a valid definition.
An elephant is an animal with 4 legs. Well, lots of animals have 4 legs, right? So an elephant is an animal. So if you have an elephant, then you have an animal with 4 legs. Being that almost every animal I can think of has 4 legs. Unless you have, well, I guess a duck would have 2 legs and wings. dog, cat, horse, cow. What did you cut them off? Well, it was just saying. Anything else? Yo. Yep. Stretching.
Yeah, I'm just.
All right. Just tight. Yes.
13.
Which one?
13.
A midpoint. A point is a midpoint when it divides a segment into two congruent segments. Okay. So 13. It's valid. So let's do this. So 13. That means congruent, the equal with the little tilde above it. So that's our statement. And then we have our converse, if this is true. So I think our statement is true or converse. If it divides a segment into two congruent segments, then it points. So that also has to be true. If that's also true, that means your inverse has to be true. That means your contrapositive has to be true, because the converse and the inverse will mimic each other, both being true. Statement is already true. That means the contrapositive has to be true. So then you have to change this to a point is a midpoint if and only if it divides a segment into two congruent segments. So that's how they stated the answer. You can't make a definite jump to a biconditional statement until you prove that your statement obviously is true. If your statement is true, that means your contrapositive has to be true. And then look at your inverse or your converse. If one of those is true, then the other one has to be true as well. Okay, so you can't just make a leap from a statement to a biconditional statement. Yeah.
I'm confused on what a biconditional statement is.
That means all of our statements, the statement, inverse, converse, and contrapositive are all true. Then we could just jump to using if and only if rather than saying if then. Okay. May I move off these? Are we good? Everyone's good on the factory? Yeah.
I have one question.
Huh?
How do you choose 12? Like, when you say something like that,
If two rays are opposite rays, then they share a common endpoint.
and I was trying to read like the reasoning, but it's not what I thought.
I'll just draw this. That would be one scenario that wouldn't work. So 12 says, if two rays are opposite rays, then they have a common endpoint. If I would then went in, so our statement is saying this. But then if we go in saying they have a common endpoint, then you have opposite rays. This has a common endpoint being right here, and they are definitely not opposite rays. So that's why we can say that it's not a biconditional statement. Because you could just have two lines drawn in two opposite directions, they can go 180 apart, which means a straight angle, which means they're opposite rays. Or I could have that scenario where I have the same endpoint, one going one way, one going a separate way. That's not 100% opposite of it. Cool? Are we good? All right. If you would, you could staple those. So perfect squares are the ones that would be the ones that are closed. All the others would be open. And this reason why this works is the factors of perfect squares is an odd number. Because you have a double root. So like 64, well, let's not go 64. 25, you have 1, 5, to 25. Those are the factors of 25, right? That's 3 factors. That means the first, the 5th, and the 25th person would do the opposite of the lockers, which then would leave it closed. Talk about the number 26. The factors of 26 are 1, 2, 13, 26. So there's 4 factors on any other number. So perfect squares are why that works. So if you take all the perfect squares all the way up through 1,000, just under 1,000, there should be, how many was there? 40, 31? 30,
You said 31.
31? Okay. Because 31 times 31 is 9.
It's 961.
961, and then 32 squared is bigger than 1,000, right?
Yeah.
There you go. That's it. All right, let's take a look at these notes for today. We are starting. Let's see, chapter 2, section 3, deductive reasoning and algebraic properties. Develop an understanding of deductive reasoning, how it differs from inductive, and then access previous understanding of algebraic properties and apply the understanding to 2-column proofs. Is this anything? Okay. All right, so first, some review. What is a counterexample? It's an example that, yeah, it goes against our claim, right? And it could just be one to make the whole thing false. Find counterexamples for each of the conjectures given. For all real numbers A and B, the difference of A and B is A minus B is less than either of the original numbers. That is, A minus B is less than A. And what do you think? For all real numbers include negatives. So could the counterexamples be some negative numbers? So if A equals -2 and B equals -3, is A minus B, -2 minus -3, that's equal to 1. Is that, nope, that right there. There's our counterexample. So that would say that A minus B is less than A. Well, no, that's not going to work. There's our counterexample. If we just throw negative numbers in there. Could have been other stuff? Sure. Okay, but I found one counterexample. For any real number A, the absolute value of A is greater than -A. For any real number A, the absolute value of A is greater than -A. So let's say we had A is equal to 4. Absolute value of 4. Oh, you know what? If I plug in 0, absolute value of 0 is absolute value of 0 greater than -0? There's no -0, so is the absolute value of 0 greater than 0? No, that won't work. There's our counterexample. For any real number A squared divided by A is greater than 1. Yeah, that gives us undefined. What about negatives? Oh, yeah, if we did a negative, if A is equal to -2, that would give me 4 on top over -2 on bottom. Is -2 greater than 1? Could do 1. 1 would work as well. So there's all kinds of counterexamples for number 3. A quadrilateral with 4 congruent sides is a square. Well, you might not know this, but a rhombus has 4 equal sides, just that the interior angles aren't 90 degrees each. So a rhombus isn't going to work there. A rhombus looks like a square that's tilted. Let's pretend I can draw. These are all the exact same size. So that's your counterexample. All right? Can I move on? Oh. Okay, boom. Deductive reasoning. Process that uses facts, definitions, accepted properties, and laws of logic to form a logical argument. Solving equations with algebraic steps would be a way to go through it. So deductive reasoning, process that uses facts, definitions, and accepted properties, and the laws of logic to form a logical argument. It's solving equations with algebraic steps. So you remember 1 and 2 and 3 step or multi-step solving of algebra 1? You know, if you had 3x plus 7 equals 8, subtract 7 then divide by 3. It's when the deductive reasoning is going through and you're saying why each step takes place rather than just showing the steps. Okay? Inductive reasoning uses observations and patterns. Okay, that's the inductive. You're walking through, touching things that are hot, saying, wow, it's hot, and there's a sign that says it's hot, so of course it's hot. Conclusions may be wrong. It's possible you see that you touched that same thing that said it was hot, and they turned the light off that one day. Well, you touch it, and it's like, oh, it's not hot this time. And then this is often used by scientists, so inductive reasoning. Deductive reasoning uses facts, definitions, postulates, theorems, conclusions that are never wrong, often used by mathematicians, and conclusions are drawn on both of them. Okay? Conclusions are drawn on both. Okay, so let's remember, inductive, we're looking at the patterns. Deductive, we actually have the rules of mathematics that we go with, or there are other rules of different science classes that we could go with. Can I move on? No? Okay, inductive uses observations of patterns. Conclusions may be wrong. Often used by scientists. Are scientists wrong sometimes?
Yes.
Do you want to know that when I was in 4th grade, I still remember this to the teeth. So Salt River Project, which was our energy company in Maricopa County, Arizona, where I grew up in Tempe, Arizona, had put out a let's save the planet type of thing for kids in 4th grade. You want to know what it's called? Global cooling. They felt that the greenhouse gases attributed to the Earth getting cooler. That was 1978. So now we're on the whole fixation of global warming because the Earth's average temperature raised 1/10 of a degree in the past 1,000 years. And people argue both ends of the thing. Which is really taking place? Well, yeah, it is. Yeah, it is. The polar bears don't have a home. Okay. Is that really the definition of global warming? Well, the polar ice caps. Let me just refer to how the polar ice caps have been melting since the Ice Age ended. Is global warming taking place? Yeah, for about the past 500 million years. Have we, as humans, destroyed it, and by using carbon footprints and changing our carbon footprints, have we changed it? That's possible. But to go on the Al Gore scare that he's driving his big ol' expedition sucking down double cheeseburgers at $1 million a minute, that's kind of a bad example to say, yes, we're having global warming. Okay? Is it taking place? Sure. Are there things that we goofed up in the environment? Absolutely. We're humans. Because I put a glass bottle in the trash can this morning that didn't go to the recycle, is the planet going to diminish any quicker? I don't know. We're on a planet, an awful big universe, a big old solar system, big old sun. Could I really interfere with it? I don't know. Maybe. Watching 20 more years, all of a sudden it's like global stabilization. Here's my only point. When the government is behind something, you need to ask this question. Who's profiting from it? You really have to ask that question. A lot of people say, oh, no, it's got to be happening because. You're right. Who is profiting from it then? If some corporation is profiting off of these studies, then I'm pretty sure things are being perverted in a way way worse than we would have ever thought. You mean you want me to believe the weather guy that is wrong about 60% of the time on the weather to say global warming is taking place because it's, half degree warmer? Y'all lived here long enough. You know that, hey, it's going to rain today. All of a sudden you got the sun out. Or, hey, it's going to be sunny skies today. All of a sudden it's dumping rain. Okay? So there's just a few things that you need to look at as far as inductive reasoning. Can we be wrong as scientists? Absolutely. Are scientists wrong? Sometimes. Do they mean to be wrong? No. They're using their evidence to support their hypothesis until their hypothesis is debunked. Is it okay? Yes. It's how the scientific process takes place. Okay? Moving on. I'm off my political stance. Man, I'm going to run out of time. All right, determine if inductive or deductive reasoning has been used in each situation. Rick likes the way the quarterback on the Razors team passed the ball in the first 2 games of the season. He decides that the team will win the season. Yeah. Inductive? Okay. Can be wrong, right? So you're looking at some patterns to make a conclusion. Sports books love this in Vegas. They do it all the time. Haley makes a list of groceries she needs to go to the grocery. Groceries she needs and goes to the website for each store in her area. She determines how much she will pay for the needed supplies using the websites. She decides to go to Piggly Wiggly, which is actually a grocery store in the Midwest, to buy. What do you think? Yeah. Deductive. You go and you look at the website and say, boom, that's obvious. That's the price. It's there. Jonathan, I'm almost done. These will be our last 2. Jonathan considers the patterns 5, 8, 11, 14, 17. He writes the equation for the linear function, then uses his equation to find a 20th number in the pattern is 62. Inductive or deductive? So he's looking at the patterns. So if you look at the patterns, you could find a 20th number by just looking at the patterns. But then inductive takes place because he found the equation. Does that make sense? And then Cindy, same idea. Cindy considers the pattern -7, -11, -15, -19. She continues the pattern. It decides the 20th number in the pattern is -83. So she just continues the pattern. So what is it? Inductive continues the pattern, right? Deductive. So this is deductive because, whoops, helps when I write. This is deductive because created the equation. This is inductive because they just kept going. They just kept, subtracting 4. Yeah.
Wouldn't it be deductive because the answer wouldn't be wrong then?
Well, you could argue that, but what if there was something that we didn't foresee in the pattern? Like, sometimes if you have a linear model and a quadratic model, they're going to mimic almost the same for a little bit of time, and then all of a sudden something gets goofy. So kind of think that way. So, guys and girls, I would say, get a start. So this week we did checking off 2, 1, 2, 2. Is there a 2, 1 to 2, 3 review?
Yes.
Yeah.
Why don't we start that? And then we'll finish this tomorrow, and we'll also finish up to the 2, 3 review. And then we will do 2, 4 on Wednesday, and then Thursday we will have a quiz over 2.1 to 2.3. And then you don't have school on Friday. Good? Yes, sir.
So our homework tonight is just a review.
Yeah, just start 2, 1 to 2, 3. It doesn't. I will not be marking it off first thing tomorrow.
So we're not doing 2.3, just the review.
Okay, why don't you just hit the review? Start looking at the review, and then we'll finish up 2.3. Yeah, we can do that. Cool? We good? Now you guys are all bothered because I talked about glow.